As we've seen, a JSON document is simply a text file which is encoded as nested sets of arrays and objects, where each attribute may itself have a value of another array or object or string or number value. So let's take a look at some of the tools that are in your belt as you make choices around how to use these structures. So first, let's consider whether and how you might use a root attribute in your document. So on the left, you see a JSON document, order123, and the entire document is a single object. But on the left, it has one attribute called order, and then all other attributes of the document are contained within it. This convention has been widely used in some circles as a way to indicate the document type. Now, by contrast, on the right, you see that order123 is still just a single object, but it has a whole series of top-level attributes within it. Now, consider the complexity of introspecting through an additional level of nesting on every single query if you take the approach on the left, versus what could be the relative simplicity of interacting with all the attributes on the right. We'll come back to this in a later lesson. Next, let's consider, should attributes be expressed as objects or arrays? Well, there's no right or wrong here, but consider in the example on the left, the shipping address attribute has a value which is an object with a series of string value attributes. And the fact that it is a shipping address is encoded in the attribute name. Now look at the example on the right, and you'll see that addresses is actually an array of nested objects. Do you know in advance how many different address types there will be? So, does it make sense for attributes to be treated extensively by making them an array versus fixed by making them a particular object with an arbitrary name? Again, there's no right or wrong here, but it's good to consider the choices available. Third, should the values in arrays be simple or nested objects? Well, again, there's no right or wrong here. On the left, we see a series of string values within the contacts array that appear rightly to be document IDs. On the right, however, we see that those values are expressed as nested objects. Now consider the distinctions here on the left. It implies there are other documents, whereas on the right, all the values are contained within this document. Let's get to attribute names. So what are some conventions? Well, first, you should use descriptive names that are self-documenting for anyone who happens to look at your document later. Second, it's good to be consistent when spacing multi-term names. Now you could space with an underscore or space using the Studley caps or camel case style that is popular in the Java programming environment. It doesn't matter to JSON, but it's good to be consistent with whatever choice you make. There's a common convention that if the value of an attribute in JSON is an array, you pluralize the name. For all other attributes, you would use singular names. You should avoid using reserved terms, and yes, there is a reserved term list available in the Nickel documentation online. So for example, you'd want to avoid use of the term user. Now, if other constraints require you to use certain attribute names that are considered reserved terms in Nickel, that's okay. You would simply escape those terms in Nickel when querying against those particular attributes. Similarly, you'd want to avoid using special characters such as hyphens. So an underscore is the preferred character for spacing when working with attributes in Nickel. Now let's consider the difference as to whether an attribute has a value, exists but has no value, is missing entirely, or is affirmatively marked null. So first, as you see here in this example on the right, a given attribute in a given document may have an explicit value, such as here, the region is Europe. And you'll find that in Nickel, you can query explicitly around this. I can filter a select statement specifically where a particular attribute does have a value assigned to it, as well, of course, as you would see in other training, where it has a particular value. But you can also query in Nickel where an attribute exists but has no value. Now here it does have a double quote. Either a double quote or a missing value entirely would both respond to a filter where we tested to see if region is not valued. But just notice that you can select based on the non-existence of a value for a specified attribute. Now, it's a different scenario if that attribute is missing entirely, but you can also filter for that in Nickel, which means that the existence or non-existence of attributes can itself have semantic meaning within your data model. Last, you can also affirmatively mark attributes as null as you could in a more traditional relational style database. So if you are porting data over, you can still work with nulls in the way that you're already used to working with them. And as you see here, you can query for a null value for a given attribute in Nickel. So what have we learned here? First, information can be encoded in many ways in JSON. It's just a text file comprised of nested objects and arrays. So we took a look at distinctions in how you may or may not use a singular root attribute within a document, or whether you might want the entire document to be a single object with all top-level attributes. We looked at choices you might make around whether to use an object, an array of objects, an array of simple values, etc. We also looked at some common attribute naming conventions, including consistent spacing, self-documenting names, plural terms for arrays, singular for all other attributes, and avoiding reserved terms and special characters unless you enjoy escaping characters in your queries. We also saw that attributes in JSON documents may be valued or not valued, they may be missing or they may be null, and Nickel allows you to query against all of these factors, meaning they can all carry semantic meaning within your data model. Next up, we're going to take a look at 4 sample physical implementations of a single conceptual model that gives further examples of everything we've discussed in this lesson. Come on back.